Imagine crossing the distance to another star in days, not thousands of years. No cryosleep, no generations living and dying inside a metal tube. Just you, a ship, and a bubble of space that moves like a wave. That sounds like Star Trek. But here's the uncomfortable part. The math behind a warp drive isn't just science fiction. On paper, it exists. And the moment you take that seriously, a darker question shows up. Because if warp travel is possible, the biggest problem might not be energy. It might be time. The same physics that could let you outrun light could also mess with causality, turn the universe into a glitchy mess, and force us to ask whether faster-than-light travel is basically a time machine with extra steps. So today we're diving into the secret truth behind Star Trek's warp drive, what the show got right, what it invented, what real physics actually allows, what NASA-style research has explored, and the one obstacle that still makes this dream feel almost impossible. And stay with me, because at the end I'm going to tell you the real price of warp drive, the part people conveniently leave out. Star Trek didn't just give us a spaceship, it gave us a promise. In that universe, humanity doesn't crawl to the stars, it surfs there. The USS Enterprise doesn't travel faster than light like a rocket trying to brute force itself through space. It bends space around it. It creates a warp field, a kind of bubble, and the ship rides that distortion. Inside the bubble, the crew feels normal gravity, normal time, normal everything. Outside the bubble, the ship is effectively cheating the map of the universe. And that idea, move space instead of moving through space, is the one part of Star Trek that hits surprisingly close to real physics. Because Einstein's rules say you can't go faster than light through space, but those same rules don't forbid space itself from stretching, shrinking, or flowing. And that's not a loophole. That's literally how the universe already works. Here's what most people forget. The cosmos has already done faster than light once right in front of us, the expansion of the universe. In the early universe, and even today at extreme distances, space can expand so that faraway regions separate faster than light, not because objects are breaking the speed limit, but because the space between them grows. Nobody is moving through space faster than light in the usual sense. Space is changing. So when Star Trek says, we're not violating Einstein, we're bending space, that's not just pretty dialogue, that's a real concept. The problem is, to bend space on command, you need an absurd level of control over gravity, energy, and the structure of space-time itself. And that's where the fantasy becomes a nightmare. In Star Trek lore, the warp drive is powered by matter and antimatter. You smash them together and convert mass into energy with ridiculous efficiency. That's not made up. Matter-antimatter annihilation is real, and it releases a lot of energy. The show also adds dilithium crystals to regulate the reaction. Pure fiction, but it plays the role of a magical stabilizer. Because a real matter-antimatter reactor isn't a campfire you sit beside. It's more like trying to hold a miniature apocalypse inside a box and politely ask it to behave. Even if you could produce enough antimatter, which we can't at scale, you'd still have to store it without it touching normal matter. And you'd need magnetic fields so strong and so precise that one tiny failure becomes instant destruction. So yes, antimatter is real, but warp core on demand is still way beyond our engineering reality. Now, let's hit the real science, because this is where the story turns from cool to dangerous. In 1994, a physicist named Miguel Alcubierre proposed a solution to Einstein's field equations, an idea now famous as the Alcubierre metric. And here's the basic concept. You create a region of space-time where space contracts in front of the ship and expands behind it, like a cosmic conveyor belt. The ship sits inside a warp bubble. It doesn't locally break the speed of light, because inside the bubble it's basically at rest. But the bubble itself can move, because it's not the ship moving through space, it's space moving around the ship. This sounds insane, and it is, but mathematically, it's allowed in general relativity. That's why people take it seriously, because it's not fantasy writing. It's a real solution to the equations we already trust to describe gravity. At this point you might think, so that's it, we found the cheat code. But here's the first mini hook you need to hear, because this is where most warp drive videos start lying by omission. Alcubierre's original model requires something we have never seen in usable form: negative energy density. Exotic matter. And no, that's not antimatter. Antimatter is still positive energy. Negative energy is weirder. It's like needing a fuel that pushes space-time in the opposite direction of normal mass energy. In regular life, energy is energy. It's positive. It gravitates, it curves space in a predictable way. Negative energy would curve it differently, like anti-gravity, in a very specific mathematical sense. And if you want to build a warp bubble, your equations scream for that negative energy like a car screaming for gasoline. No negative energy, no bubble. But wait, you might say, don't we see negative energy in quantum physics? Kind of. In certain quantum effects, you can get tiny regions where energy density is lower than the surrounding vacuum. People often bring up the Casimir effect as a popular example, but the key word is tiny, microscopic, fragile. And quantum theory also comes with rules that seem to limit how much negative energy you can isolate, and for how long. It's not like you can just gather a mountain of negative energy in a tank and pour it into a warp engine. So even if the universe allows negative energy in principle, it might restrict it so hard that warp drive becomes physically impractical, like allowed by math, forbidden by reality. And it gets worse. Even if you somehow had the exotic matter, the energy requirements in the original Alcubierre proposal were ridiculous, often described as comparable to the mass energy of a planet or more. Think about that. Not a lot of fuel, not a big reactor, a civilization-level power source, something closer to a star than a spaceship battery. That's why warp drive stays in the realm of theory. It's not one problem, it's a stack of problems, and each problem is a boss fight. Now here's the next twist, and this is where modern research tries to pull the dream back from the dead. Later, physicists explored variations of the Alcubierre concept. What if the bubble shape is different? What if it's not a simple sphere, but a more optimized geometry? What if you flatten the bubble or adjust the field distribution? Some calculations suggest that changing the warp bubble's shape could reduce the energy requirements dramatically. Not easy, not small, but potentially less absurd than planet mass. That's where you'll hear names like Harold Sonny White associated with the idea of refining the concept. And this is important. When people say NASA built a warp drive, that's not what's happening. The real story is far more cautious. Researchers explore whether the math can be adjusted in a way that makes the requirements less impossible. That's not a ship, that's not a motor, that's a blueprint being argued over in a chalk war. So what has NASA actually done? There have been research groups and labs that looked at advanced propulsion concepts and tried to test related ideas, often in the category of breakthrough physics. The big idea you might see online is that some experiments explored whether you could detect tiny space-time effects or energy density patterns that resemble what a warp field would require. If you hear that someone created a warp bubble, understand what that means in responsible terms. Not a bubble you can fly through, more like a microscopic theoretical analog, a structure or measurement that resembles a predicted distribution in the math. It's like drawing a tiny ripple in a cup of water and saying, this shows waves exist, not we built the ocean. Still, even that kind of analog work matters because it pushes the conversation from pure fiction into testable questions. And in science, testable questions are everything. But now we reach the part that turns warp drive from a dream into a horror movie. Because even if you solve the energy problem, somehow, even if you solve the exotic matter problem, somehow, there's a deeper problem hiding in the shadows. Control and causality. Here's a simple way to think about it. The warp bubble could create regions where information can't easily enter or leave. In some models, the front edge of the bubble acts like a horizon, a boundary. That means the crew might not be able to control the bubble from inside once it's moving at superluminal effective speeds. Let that sink in. You build the most powerful engine in history, and then you might not be able to steer it, or stop it, or even know what's in front of you until it's too late. Imagine driving a car at insane speed while your windshield is blacked out and your steering wheel is disconnected. That's not interstellar travel. That's a ballistic missile with a coffee machine. And if you can't communicate through the bubble the way you want, navigation becomes terrifying. How do you adjust course? How do you avoid obstacles? How do you coordinate with mission control? This is the kind of unglamorous detail that destroys the sci-fi fantasy, but makes the physics conversation real. And now we hit the biggest psychological punch in the whole topic. Faster-than-light travel is deeply tangled with time travel. People hate hearing this because it ruins the vibe. But it's not a conspiracy. It's a feature of relativity. In many frameworks, if you can send information faster than light, you can create scenarios where information arrives before it was sent, depending on reference frames. That leads to paradoxes, the classic grandfather paradox territory. And even if warp drive isn't exactly moving through space faster than light, it can still effectively allow superluminal travel relative to external observers, which puts it in the same danger zone. So the universe might enforce a kind of cosmic censorship. Sure, the equations allow it, but the real world might block it through energy limits, stability issues, or quantum effects that prevent paradoxes from ever happening. In other words, the speed of light might not just be a speed limit. It might be a reality protection system. So let's talk about stability, because this is another retention hook most people ignore. A warp bubble isn't just a warp bubble. It's a highly engineered distortion of space-time. That distortion could interact violently with radiation, particles, and the quantum vacuum. Some theoretical work suggests that if you create horizons, like the front edge of a warp bubble, you might trigger extreme energy buildups, potentially releasing intense radiation when the bubble collapses. Imagine traveling, then dropping out of warp, and unleashing a blast of high-energy radiation in front of you like a cosmic shotgun. That's not just a problem for your ship. That's a problem for anything you arrive near. If warp drive is real, it may come with a built-in weapon you didn't ask for, and that is why serious researchers treat this topic carefully, because the details get dark fast. Now, to make this feel real for your brain, let's do a thought experiment. If warp travel worked, what would it feel like inside the bubble? From the crew's perspective, maybe almost nothing changes. No extreme acceleration, no crushing G-forces. That's one of the most seductive parts of the concept. You're not accelerating through space. You're riding a wave. You could be sipping coffee while the universe is bending outside your window. But what would you see outside? Depending on how the bubble interacts with light, the star field might distort, like gravitational lensing. Stars could smear into arcs. The universe could look like a fisheye lens. Brightness could shift, and navigation by sight might become meaningless. You might not see ahead the way you expect, because ahead is a region of contracted space-time. And if communication is limited, you're isolated in your own pocket of reality, alone, moving, and not fully sure what's waiting when you exit. And here's the next mini-hook. Even if warp drive doesn't kill you, can your ship survive the environment it creates? Space is filled with particles, dust grains, cosmic rays, hydrogen atoms drifting in the void. At normal speeds, that's manageable. At relativistic speeds, tiny particles become bullets. At warp-like effective speeds, the physics of what happens to incoming particles could be chaotic. Some models suggest you might accumulate particles at the front edge of the bubble, compressing them, heating them, turning them into a dangerous energetic wall. That means warp travel could come with a constant risk of frying yourself with your own collected debris. Again, not a cinematic montage, a real engineering nightmare. So why even talk about this? Because science fiction has always worked like an advanced scouting drone for the human imagination. Star Trek came out in an era when computers filled rooms and phones were wired to walls, and yet the show imagined handheld communicators, tablet-like devices, automatic doors, and a future where humanity explores instead of hides. That matters. Not because fiction predicts the future perfectly, but because it gives engineers permission to chase ideas that sound impossible. It takes a dream and makes it feel like a destination. And warp drive is the ultimate example of that, because it forces physicists to ask, what does Einstein's theory truly allow? That question alone has value, even if warp drive never becomes practical. Sometimes you don't get the exact invention you wanted, you get the breakthroughs you needed along the way. Now let's make it brutally honest. Are we close? No. We are not close, not even a little close, and we don't have negative energy in usable quantities. We don't have energy sources anywhere near what would be required. We don't know how to stabilize a warp bubble. We don't know how to control it safely. And we don't know how to prevent the causality problems that show up when you start playing with superluminal effects. But here's the hopeful part. This is not just impossible forever. It's impossible with our current tools. And history is full of things that were impossible until the toolset changed. 100 years ago, splitting the atom sounded like wizard talk. Today, it's a reality, dangerous, complex, and controlled, but real. 200 years ago, powered flight looked like fantasy. Then it wasn't. And if you want a traditional truth that always holds up, it's this. The future belongs to the people who keep showing up, keep testing, keep learning, and keep building, brick by brick. The universe doesn't hand you warp drive because you want it. It hands it to you because you earn it through relentless progress. So where does that leave us? Right on the edge of a cliff between dream and reality. Warp drive is one of those ideas that acts like a mirror. It reflects how bold we are and how limited we still are. The math whispers, it might be possible. Engineering screams, not yet. And the deeper physics warns, be careful what you wish for. Because if warp drive becomes real, it doesn't just change travel, it changes causality, it changes warfare, it changes the meaning of distance. It turns the galaxy from a set of isolated islands into a connected ocean. And if we ever cross that line, humanity won't just become an interstellar species. We'll become a species that edits space-time, like programmers editing code. And that's not just exciting, that's terrifying. So here's the conclusion I want you to sit with. Star Trek didn't give us warp drive as a cool engine. It gave us a philosophical weapon. It taught millions of people to ask, what if the rules are different than we assume? Alcubierre showed that the rules might be bendable on paper. Modern research shows that the conversation is not totally dead. But the price, the real price, may be that you're not just traveling faster than light. You're stepping into a region of physics where time can be manipulated, horizons can trap you, and the universe can punish mistakes with violent consequences. Warp drive might be possible, but it might also be the most dangerous technology a species can ever touch. And now I want to ask you something. If warp drive became real tomorrow, fully stable, fully controllable, where would you go first? Another star? Another galaxy? Or would you be too afraid to step into a machine that bends reality itself? Drop your answer in the comments. I read them all, and your idea might shape the next episode. If you want more science, mystery, and the future of humanity, subscribe to the Sirius Hub. Because out here, the universe doesn't care what we believe. It only cares what's true. And we're going to keep chasing the truth, one impossible idea at a time.